In 1934, pharmacologist Otto Schallmann synthesized a new compound called meperidine. During testing, he noticed something highly specific. The mice injected with the drug all exhibited an identical S-shaped curve in their tails. Schallmann had previously seen this exact physical reaction only once before, in mice injected with morphine. Based on this single shared physical trait, he deduced that meperidine likely shared morphine's narcotic pain-killing properties. He was right. We now know meperidine as Demerol. This leap in logic relies on ampliative reasoning. Ampliative reasoning is a formal argument structure where the conclusion extends beyond the premises, meaning the result is supported by evidence but is not guaranteed to follow with absolute deductive certainty. It lacks absolute certainty, yet this specific mechanism dictates how judges establish case law precedent, how AI models map relationships, and how physicists model the unobservable. Analogical arguments function as precise, evaluative logical mechanics, providing the structural justification for scientific inference into the unknown. To evaluate whether an analogy actually holds up, we have to strip away the prose and translate it into a formal architectural map. An analogy maps a source domain of known properties to a target domain of unknowns. Horizontal relations map similarities directly across the gap between them. Meanwhile, vertical relations are the causal dependencies within a single domain. This structure introduces a severe philosophical conflict. If the target domain is inherently uncertain by definition, by what exact metric do we judge if these horizontal and vertical mappings are logically sound? The history of cognitive science and epistemology is defined by a deep schism over the answer to this question. Does the validity of an analogy rely on shared physical substance or on pure mathematical syntax? The intuitive approach is to assume that the strength of an analogy depends strictly on the total number of shared features. We count the similarities, and if the number is high enough, we accept the conclusion. But this metric is deeply flawed. Consider the philosopher Thomas Reid. In 1785, Reid used an analogy to argue for the existence of life on Mars, basing his conclusion entirely on the planet's similarities to Earth. If we map Reid's argument onto our table, we start with the positive analogy, denoted as P. This block contains the known similarities. Both planets orbit the Sun, both have gravity, and both revolve on an axis. We also have to account for the negative analogy, or the known differences between the domains, such as atmospheric composition and temperature, that must be weighed against the similarities. Finally, we map the hypothetical analogy, denoted as Q star. This is the final leap, inferring that because Earth supports life, Mars must support life as well. Philosopher Mary Hess rejected this method of simply tallying up traits. She introduced the causal condition as a strict constraint. The vertical relations in the source domain must be causally related to the hypothetical analogy. Having an orbit and having gravity do not directly cause a planet to support life. Without a demonstrable causal grounding between the shared traits and the inferred trait, a material analogy is just a statistical coincidence. It is not a valid inference. But cognitive scientists approach the problem from the exact opposite direction. What if the physical, causal content of an analogy is entirely irrelevant to its logical validity? Psychologist Dedra Genter established a framework to test this, culminated in an algorithmic model known as the Structure Mapping Engine, or SME. This diagram shows how SME evaluates analogies through systematicity. Systematicity is the principle that an analogy is strong if it matches the syntax of higher-order relations, operating totally agnostic to the actual material or objects being compared. This leads to the systematicity principle. Mappings that place deeply nested, mutually interconnecting relationships in correspondence yield mathematically stronger inferences than isolated feature matches.
The structure itself is the proof. High-order relational matches can generate highly systematic, yet physically absurd analogies if they ignore the type of causal relevance, specifically whether a cause is positive or negative. Freezing temperatures on ancient Mars might map structurally to freezing temperatures in Antarctica, but extreme cold actively prevents complex life rather than supporting it. Pure syntax without material context risks generating logically flawless models that fail entirely when applied to the physical world. To evaluate an analogy accurately, We need a framework that demands both Hesse's causal reality and Gentner's structural rigor. Philosopher Paul Bartha proposed a hybrid solution called the articulation model. Bartha outlines two necessary conditions. The first is prior association. This requires an explicit, demonstrable connection in the source domain between the known similarities and the projected hypothetical analogy. The second condition is the potential for generalization. This requires proving there is no critical disanalogy in the target domain that would block the transfer of the logic. A critical disanalogy is any distinct difference that directly interferes with the causal relationship established in the source. A rigorous scientific analogy must explicitly map the causal dependencies within the structure. It has to prove that the target domain is actually capable of hosting the source's logic. This brings us to the ultimate epistemological hurdle. If an analogical argument is built perfectly, does it actually confirm a hypothesis, or does it simply make the hypothesis worth investigating? We have to distinguish between modal plausibility, which establishes initial prima facie grounds for further physical investigation, and probabilistic plausibility, which provides concrete mathematical support to shift actual scientific belief. This equation shows the Bayesian confirmation model. It is the standard mathematical framework used to update scientific belief based on the introduction of new evidence. Within the formula, E represents evidence and K represents existing background knowledge. To confirm a hypothesis, the probability of it being true given the evidence and background knowledge combined must be greater than the probability given the background knowledge alone. But analogical reasoning runs into the problem of old evidence. Because analogical arguments rely entirely on mapping data that is already known in the source domain, the evidence is already part of the background knowledge. The equation stalls. According to strict orthodox Bayesian conditionalization, analogical reasoning cannot provide novel mathematical confirmation of a hypothesis. Yet modern cosmology is utilizing a cutting-edge workaround to this exact limitation, a concept known as analog confirmation. Researchers like Radin Dardashti have published theoretical work on using analogical reasoning to study completely unobservable phenomena, specifically black holes. Because black holes destroy the light necessary to observe them, physicists have created acoustic dumbholes. These are fluid dynamic models running in laboratories that physically mimic the mechanics of event horizons. This relies on formal analogy, or nomic isomorphism. Nomic isomorphism occurs when the physical laws governing two different systems have the exact same mathematical form. Because the equations governing ideal fluid flow and quantum field theory share identical structural syntax, they are formally analogous. This leads to a highly controversial epistemological claim. Philosophers argue that observing analog Hawking radiation inside the lab's fluid model generates entirely new evidence. If the math is isomorphic, data generated by the analog provides actual Bayesian confirmation for real black holes. The formal architecture of analogical reasoning allows researchers to bypass the limits of direct observation, translating laboratory fluid dynamics into a mathematical confirmation of the unobservable universe.